Okay, Ben Siemens with us. Good deal. Wonder who else is with us. Darren Turner, we've got a class.
Good morning.
Good morning. It looks like a beautiful day out there. It's going to be 50 today.
Things are looking up, huh?
Things are looking up. How many more weeks of school is there? Do you know?
2, 3. I really don't know. I'm kind of just going day by day, you know.
I think this is the last actual week of lectures. So it's kind of sad. You're just going to have this one here, and then my wonderful Thursday morning lecture, and then I think your final is going to be next week. Let me put down here whatever homework and all that we have. Totally organized as always. Yeah, today's the 1st of December. We're doing Moore's Circle today. And you're supposed to do a Moore's Circle worksheet number 1 for homework. Does that sound right? I don't know. Today is December 1st. I think there's a Moore's Circle worksheet online. I think I put it on content. There's 2 of them. I thought we could do some of them together, and you could finish them and turn it in for homework. That was my intention anyway. Okay, December 1st. All right, the way I understand it, you're going to do your homework. This will be homework, gosh, which one is this? Kind of mixed up here. Let's see. We'll get it figured out. We're going to get it figured out. Now, homework number 28 was chapter 8, problem 2 and 10. Let me write some stuff down so I can figure this out. Homework number 28 was chapter 8, 2, and 10. All right, that was 28. Okay. And then, so I think I think homework number 29 will be the Moore's worksheet. I think there's 2 worksheets. A little bit confused here. But that sounds right. Okay. See, I think chapter 9 is all about transformation equations, isn't it? Let me look and see. Yes. And we're going to do that worksheet for homework number 29. Are we going to do the worksheet number 2, though, is the question. Don't know. Don't know the answer to that. And when will this be due? Probably, if this is Tuesday, it would be due Friday, which is the 4th. Yeah. The 4th of December. We're in December now. I think I gave you 2 of these worksheets. I guess I could give you the other one for Thursday. We'll see. Well, if you have content, you could pull up that worksheet, and let me pull up mine, and we can do some of these together. I'll tell you what this looks like. It looks like, I don't know if you can see that, but it kind of looks like that. There you go. Yeah, you can see that. I think we should do some of those. Maybe on worksheet 1 and 2. We'll play it by ear here. Sorry to be not totally organized, but we're getting there. Okay. Now, before I start doing some of these, did you have any questions? Well, let's see who's on board here. I'm going to look and see who's in the class right now. Oh, we got a good class. We have Alex, Ashley, Ben, Braxton. We have Samuel, Mohammed, Julian, and Darren, and Brian. Got a great class. Okay, well, dig out your Morse circle there. Why don't we do a couple of these on this first worksheet? You should have that on content. I just wonder, have any of you pulled up this worksheet on content? If you have, let me know. Did you find this?
Yeah, I find it.
Was that a yes?
Yeah, I find it.
Good. You have them there. All right, great.
Yeah.
Well, let's do some of these, a couple of these together, and you can finish those for your homework. Let's do number 2 together. Okay. Well, we're on home worksheet number 1, and problem number 2 has a stress element. They call these stress elements. And it has a stress element like this. See, it's got compression in the Y and tension in the X, and it's got some shear stress in the XY equal to 5 KSI. This is problem 2. What we're doing right now is we're doing problem number 2 on the Moore's worksheet number 1. It's due Friday. You're supposed to do this. You do the others. I'll do this one. And then maybe we could do one on the worksheet number 2. I'm looking at a worksheet like this, and I'm doing problem 2 right now. Okay. Now the way you do this is you draw an axis. You draw a shear stress axis. Here we go. Da-da-da. This is going to be, no, that's the normal stress axis. And this is going to be the shear stress axis. There's your shear stress axis. And then there's a step-by-step procedure in your book. See, what we're trying to do is find the maximum stresses in your piece. Now this stress element, it looks like the maximum stress is 8 KSI, but not necessarily. It might be bigger than that. And here's how you do it. You put 8 KSI on here. I'm going to use centimeters. So I'm going to go here to 8. There's 8. And you see that 5 shear stress going up? Well, the shear stress axis goes down. So you have to go 5 going down. You go down to here. It's right there. Boy, Jove. See, I measured that. That's got 5 centimeters going down. Now this right here, I'm going to label it point A. That's my anchor point. All of your angles are measured from that point.
Mr. Griffin,
Yes, go ahead.
I think that 8 KSI it's not 8, it's 4 KSI on the sheet.
Oh, wait a minute. Auga. Well, mine says 8 KSI. Yours says 4 KSI. You're looking at number 3, aren't you? My number 2, I have a sheet here, and my number 2 has an 8 KSI right there. And Mohammed, you're saying it's 4 KSI? Earth calling Mohammed. Come in, Mohammed.
Yes, on the Mohr sheet number 1, on the
Yeah.
second one, 254.
It says 254?
Uh-huh.
Really? So I gave you the wrong one?
Our sheet looks a little different than yours.
Yeah, our sheet is different from you.
We have
Oh,
ABC.
oh, you have ABC.
Mm-hmm.
Huh. You don't have one like this. Well, let's do the one you have.
A is really similar besides one number.
Uh-huh. So,
The
so this,
the shear XY is 3 KSI instead of
okay,
5.
well, here, we'll change it. I don't know how I managed to goof up here, guys. I'll have to look at my content and see what I gave you guys. But the shear is 3. What about this one?
It's 8, but it's in a different, it's pointing down.
Well, no, this either goes left or right. It can't go down.
Oh, no, that's right. That's right. I meant the shear XY is going down.
Oh, okay. Well, we can do that. The shear is going down. Like this. Man, I'm sorry to screw this thing up so bad. Oops. I'll get it right here in a minute. Well, what about this? Was this 2?
Yeah, that was 2.
What, and it's compression?
Mm-hmm. Wait, no, that's no, it's pointing the other way. The
Oh, it's
yeah.
going this way. The 2 is going this way. Man, totally screwed up. It's going that way. Now do I have it like you have it?
I think that looks good.
Mohammed, is that the way you have yours?
Yes, sir.
Now, what, Mohammed, you were talking about 4 KSI. What are you talking about 4 KSI? Where's that?
That was a B.
Oh, okay.
Yeah.
And what is this, problem A?
Yeah, this is problem A.
Oh, gee. Well, I'll look on content. It really doesn't matter. You guys, you do the sheet that's on content, whatever it is, and it'll be all right. But now we finally have it the way you guys have it. Okay. Well, here's what you do. You go over 8, but you don't go down. You go up. You go up 3. So here we go. We're going to go up 3, right? That puts me right here. And there is my anchor point A. Now this is 2. See, this was at 8. And now we're going to come over 2, puts me right here. There's 2. And if you go up 3, you have to go down 3 on this one. So this puts me right here. Now we can draw our diameter of our Mohr circle. Here we go. That's it. See, now if this is 8 and this is 2, what that means is you got 6 there. I don't think I drew that very good. So this should be 3 and that should be 3 because it's half a 6. Yeah, let me make it a little bit nicer, maybe. More like that. Oops. Not that extreme. Yeah, that looks pretty good. You got, this goes down 3. That's 3. This goes over 3. That goes up 3. Hey, you know what that is? That's 3 square roots of 2. Well, let me figure out what that is. 3 square roots of 2 is 4.243. this radius of this circle is 4.243. There we go. KSI. Now we're going to draw the Mohr circle. Well, here's our center, and it's 4.243, so it'll kind of come up to here. 4.243, yeah, like that. And 4.243, like that. And we're going to draw a Mohr circle now. Come on now. Ta-da, and there. We've got our Mohr circle. And here's the points of interest. Right here is your maximum normal stress. And it's not 8, it's a little bigger than 8. I can tell you how much it is. If this is 2 and that's 3, that puts this here at 5. And if the radius is 4, then if you add 5 to the 4, you'll get 9.243 KSI. That should be your maximum normal stress. The maximum normal stress should be 9.243 KSI. Right here you have the maximum shear stress, and that is 4.243. It's just the radius of your circle. Okay, now let's check that with the transformation equations. Well, you look in your book in chapter 9, and you'll find the transformation equations. Let's just check one of them just to show you that this stuff does work. Yeah, but where are my equations? Just a minute here, let's see. Okay, here they are. Well, yeah. Let me write it here. Now this is the normal stress at a different orientation other than XY. It's been rotated, and it's equal to you'll find these transformation equations in chapter 9. Okay. Wait a minute, that's not all. Well, there it is. It's pretty long equation, but it doesn't scare us. Now, see what we got here is we got 8 and 2. That makes 10 divided by 2 is 5. So this whole thing here is 5. And this is 8 minus 2. That's 6 divided by 2 is 3. Now, what about these angles? Well, if this is your anchor point, this angle here is 45 degrees, only it's clockwise, so it's negative. This is a negative 45 degrees. The shear stress is 3, but now wait a minute, it's going down, so that's a minus 3, and this is sine of 45. Let me write it up here for you. We'll write it up here. We're saying, in this case, it'll be the maximum normal stress. Should be 5 divided by 2 plus, well, no, wait a minute. No, just 5. It's 5 plus 6 divided by 2 is 3. I'm going to confuse myself here. Times the cosine. I believe it's minus 45 minus 3 sine of minus 45. Okay. Put all that in your calculator and let's see what we get. Here we go. Well, boy, Juve, I'm getting 9.243 KSI. Yay, we figured out the maximum normal stress on this stress element, and it's not 8, it's 9.243. Okay, well, let's do some more. We're going to do some more.
I have a question.
Yeah, go ahead.
Why don't you multiply the angle by 2?
The angle that we're using is right. It's a double angle. This angle is 2 theta. Thank you for asking. Theta is actually a negative 22.5.
Oh, okay.
And so if you rotated this a negative 22.5, what you'd have would be, I'll kind of fake it in here. You would have an orientation like that, where that has been rotated 22.5 degrees clockwise. And you would have a normal stress acting on that stress element that's been rotated of 9.24 KSI. Interesting. Well, let's try another one. Okay, I'm going to erase all this and we're going to try another one. Here we go. That was a good question. Any other comments or questions?
Professor, how do you know that the 3 KSI of the shear stress are upwards going from the 8 and downwards going from the 2 and not the other way around in the Morse circle?
Okay.
You have 8 KSI in your X stress mark there, and then you go up the 3 KSI of the
Yes.
stress. How do you know it's up and not down?
Who am I talking to?
This is Samuel.
Samuel, thank you so much, Samuel, for asking that. To explain it, I would have to derive this equation here. This is called a transformation equation. And I would have to derive that. What they did, Samuel, was they added up all the forces in the x prime direction and set them equal to 0. And to do that, you've got to, on the shear stress, if it's, this is kind of a habit after a while. If the shear stress is going up, then on your Morse circle it goes down. And if the shear stress is going down, on the Morse circle, it's going up. It has to do with the derivation of the stress transformation equation, that's hard for me to say, and how Moore translated that into his circle. I guess, well, follow the directions. They have a step-by-step direction, but here, let's do some more, and then I think maybe just by habit you'll be okay. Okay, we're going to do another one now. And this one, let me make some room here. But you guys do have a worksheet. It might be screwed up from what I thought I gave you, but you do have a worksheet, and that's what I want you to do for your homework. And I think you can send it in on Blackboard. I believe you can. But because there should be a link there. Okay, now this is not on your worksheet, but it's the one I want to do right now because I want to show you this. And here's my stress element. And this is the one I wanted to do, but thanks to my excellent students, they told me that's not what they have on the worksheet. I don't know what I did. But we'll bear through this. There's not much school left. We'll survive somehow. The main idea is to find the maximum stress. That's what the main idea is. Okay, now we have a stress element, and we're going to draw the Moore circle. We're going to find the maximum normal stress, and the way you do that is you draw a normal stress axis. That's the normal stress axis. And then this is going to be the shear stress axis. And then if this is 8, you go over 8. You go over 8, that's positive, so you go over 8 to right here. You know, that's good. And then the shear stress goes up, so you go down 5. All right, I'm going to go down 5. That puts me right here. Now, that's going to be my anchor point. And we'll actually, we'll get some angles out of that. I didn't do that last time. Now this here is compression. See that 2 KSI? That's negative. So you have to go over here 2 spaces. Well, I'm using centimeters. There, that's pretty good. And then if that went down, this has to go up. It has to go up 5. So that puts me right there. By Jove. And then you draw your diameter of your Moore circle. Here goes. Diameter of the Moore circle coming up. That should be it. Now let's see. Remember, this was 8. This went over to -2. So 8 and 2 make 10. So that means this here is 5, and that's 5. Because half of 10 is 5. So you got 5 here. Well, this is 5, and that's 5. Hey, that's another one of those 45-degree angles. Can you read my writing? That's supposed to say 5. 5. This is 5. These are all KSI. That's a -2. And so the radius of our Morse circle, you can do it this way if you want. 5 squared plus 5 squared, square root. That's going to give you the radius. Let's see what that is. I'm getting, we should have done that in our heads. It's 7071. That's one of our familiar old numbers that we've seen before. That's the radius. So here, let me draw my circle now. Here's the center. And you come over here, 7, right there. 7, yeah, right there. 7, put you right there. 7, put you up here. 7, and 7. All right, it's time to draw the circle. Here goes. There you go. Well, it's a little messy, but not too bad. Okay, we've got some points of interest here. This point right here, that is your maximum tensile stress. You know what this is right here, this point? That's your maximum compressive stress. That might be of interest. See, this is tension here. And right here, there's your maximum shear stress. That's important to us too. You'll find these in our equations. You know how it goes. There's an equation that goes like this. And there's another one that goes like this. And then there's one that goes like this. And then there's one that goes like this. Now, we've studied all of those. We've studied all of those, haven't we? And see, the maximum is right there. Now, who knows what causes it, because we would have to go back and do our free body diagram, solve for all the external forces and internal forces, and then solve for the stresses in the X and Y directions. But see, the Morse circle, what we're studying now, we're trying to find the maximum. And look, there's some compressive stress. Okay, well, let's get it. Well, let's see. If this is 8 and that's 5, that means this is at 3. The center of that thing is at 3. Yeah, that sounds right. So where is this at? Well, it'd be 3 plus 7071, wouldn't it? See, that's the radius. So add them up, you get 10.071. The maximum tensile stress is 10.071 KSI on this thing. Now, what about the maximum compressive stress? Well, now let me think about this. You'd have to take 3 and subtract the radius. See the radius? Here's the radius. What's 3 minus the 7071? I think it's minus 4071. I did that in my head. That's kind of dangerous. But I think that's right. If you take 3 and you subtract 707, yeah, that's right. So that's the maximum compressive stress. Now the maximum shear stress, well, that's just the radius of the circle. That's 7.071 KSI. Now let me show you where the angles are at. And these are double angles. All angles are measured from this point A. Now to get up to here, that's a positive 45 degrees. So this maximum shear stress that's a double angle. It occurs at 45 degrees. So it occurs at an angle of 22.5 degrees. No, that's not the maximum shear stress. The maximum normal stress is 10.071 KSI, and it occurs at an angle of 22.5 degrees because this angle here, this double angle, is 45. Now, if you want to know the maximum compressive stress, well, you can either measure your angles going this way, like that, or you could go like that. It would be negative. I'll tell you what that angle is going that way. I think it's 225. What's 180 plus 45? I think it's 225. That's your double angle. So the maximum compressive stress is 4.071 KSI, and it occurs at an angle of half of that, which is 112.5 degrees. You could rotate it counterclockwise. That's a positive rotation. Let's just plug that in so we can show you, okay? Here, let's, I lost my equation already. Let me see if I can find what I did with it. We'll plug it in and see. We'll see if I'm lying to you here. Oh, okay, I'll need some room. There's some room. Let's do this. Now we're talking about, I thought we'd show you the maximum compressive stress. That could be of interest. See, some things are real good in compression, like bricks, for example. Bricks are good in compression. They built very tall buildings back in the old days out of bricks. Okay, now here's the equation, the transformation equation. Now let's plug in our numbers and see if we get this answer. That would be fun to do. Okay. Well, what's sigma x plus sigma y? Well, it would be 8 minus 2. That gives you 6 divided by 2 is 3. So this is 3. That makes sense? I think so. You see, this is 8 minus a minus 2. That makes 10. 10 divided by 2 is 5. Now, the angle that we're talking about here, if you're doing the maximum compressive stress, I think is 225. Plus the shear stress, which is 5, times the sine of 225. Well, there's all of our numbers in our transformation equation. We're going to plug those in. I'll shut up for a minute. I think we did that right. Plug that in and we'll see what happens. Go for it. I want you to plug this in. We're solving, in this case, we think, for the maximum compressive stress. Okay, let me call on one of my excellent students. What we're doing right now is we're plugging in this equation, and here's our numbers. And let me call on my friend Alex. Unmute and say hello, please, Alex.
Hello.
Did you plug that in? What'd you get?
I got negative 4.071.
You know what, Alex? That's what I got.
Yay.
Yay! And you know what? That's what we got from the Mohr circle, negative 4.071 KSI. Yeah, and now the angle is 112.5. The double angle is 225, but that's the double angle. So if you rotated this thing counterclockwise, 100, well, that's really more than 90, isn't it? That will give you your compressive stress. And we could go and show you that the maximum tensile stress is 10.071. Here, let's do that. That sounds like fun. Let's do that. Well, this doesn't change. That's still 3. This doesn't change. That's still 5. It's just that this angle here won't be 225 anymore. It's just 45. See it? All angles are measured from this anchor point. So you go up 45. Here, let's change that. Put in 45 degrees. Change that. Put in 45 degrees. Now solve this. And let's see what we get. Okay, can you read my writing? That's supposed to say 45 right there. Well, we're trying to find this maximum tensile stress now. See, this, we did the compressive stress, but right now we are trying to find the maximum tensile stress. Go for it. Let's see what happens. Well, I did that. Let me go to another wonderful student here. Let me go to my friend Ashley. Ashley, unmute and say hello, please, Ashley.
Hello.
Hey, Ashley, did you plug in this 3 plus 5, blah, 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 plus blah, blah, blah? What'd you get?
10.071.
Well, that's what I got. How about that? And you know what? That's what the maximum tensile stress is. It's 10.071. We did good. And the angle, well, the double angle is 45, but the angle is 22 and a half. So if you rotated this 22 and a half, kind of hard for me to draw, but I'll try. There, I rotated it probably more than 22 and a half. But you have a normal stress here, and that's the maximum of a 10.071. It's bigger than 8. Interesting. Well, we could do a lot more, but I'm starting to get bored with this. I thought maybe we could move on and talk about buckling, but we could do it. We could do some more if you want. Tell you what, you do those. Go to content, and for homework, I think there's a link there, and you're going to do some problems there. I think we did one of them here just a little while ago. So you only have 4 to do. And they don't take long. Any questions before we move on to something different? Any comments or questions?
Mr. Griffin?
Yes.
So on the homework, it says we have to do the Mohr sheet number 1, but we have 2 sheets of Mohr circles. So do you want to do both?
Just do one. We did, I think, number 2, Mohammed. So just do the other 4 problems. And
Okay, so on the sheet number 1, we only have 3 problems, A, B, and C.
oh, is that all?
Yeah.
Are you lucky people? You only have to do 2 problems for me then. Yeah, do that. Turn it in. If you get those right, I'll be happy, and I'll give you your 4 on your
And
homework.
also, do you want to see those equations as well in the Mohr circle?
No, you don't. You don't have to, unless you want to. You can do that to check it. Okay, well, I'm going to erase this. Any other good questions? Those are good questions. All right, well, here, let's say goodbye for now to stress transformation equations in the Mohr circle. Now you guys need to know something. This was all, they came up with this way before computers. They've got computers now that do all of this for you. And see, people out there in the real world, they're probably not drawing more circles anymore because the computer does all that for them. But it's nice to know where in the heck what's going on. That's the computers are using the knowledge that we're showing you here with these Mohr circles. And I don't want you to go out into the world ignorant about the fundamentals. So at least you'll know, hey, we did some Mohr circles. Yeah, I can do one. But right now we're going to talk about buckling. The topic right now is buckling. And it's in chapter, I don't know, let me dig around here and see. Actually, it's in chapter 13. Buckling is important because it's one of the ways that a structure can fail. There was a hotel in Kansas City, I think about 30 years ago, that there was buckling and there was a collapse and people were buried under the rubble and they had to get cadaver dogs to find them. What's interesting about that collapse in Kansas City, you might have heard about it. They had a balcony and they had a whole bunch of people up on that balcony and they exceeded the capacity of that structure and it failed due to buckling. what was interesting is my wife and I were there 1 week before it happened. I could tell you the whole story, but we don't have time. But buckling was, the equation for buckling was figured out by Euler. You might have heard of him. He was a famous Swiss mathematician, and you might run across some of his work. But you can read about it. This is all derived on, it's around page 660, 670, 671. And what we're going to talk about is Euler's equation for buckling. And here it is. This is called the critical load. It's the critical load, or the Euler load. If you exceed this critical load, your column, and we're talking about columns now. And let's see if I can demonstrate this for you. I've got my ruler here. And if you have too much force on that ruler, it will buckle. You see, I'm pushing on it. Well, it's kind of hard, but the idea is it starts to bend. If that column starts to bend, you got a problem. The whole thing could come down. But if you press hard enough, I can't do it hard enough. But if you press hard enough, it will buckle. Now it can buckle several ways. It can buckle like this, or it can buckle like this. But in any case, if you exceed this load, it will buckle. Now, you know what L is. It's just the length of your column. You know what I is. It's the moment of inertia of your column. And you know what E is. It's your modulus of elasticity of whatever material that you have. So let's just show you that. And now you need to know something about this I here. See this ruler, it's really pretty easy to bend this way. See how I'm bending it this way? It bends real nice this way. But it doesn't bend so good this way. I'm trying to bend it, but it just won't. You know why? Because the moment of inertia about this axis is so big, it doesn't give. But the moment of inertia is much smaller about this axis, and it will bend. You always want the smallest moment of inertia. Here we'll just practice and show you. Suppose you had suppose you had a 2x4. Okay, a 2x4. You're all familiar with 2x4s. There you go. 2x4. Suppose it's 8 foot long. Eight foot long, 2x4. You know what? That looks more like a 2x6 or a 2x8, doesn't it? Doesn't look like a 2x4. Let me try to draw it better. A 2x4 would look more like, yeah, that's better. Yeah, that kind of looks like maybe a 2x4. Okay, now you got 2 inches here, 4 inches here, 8 feet here. And you've got a cone. And that 2x4, if it's going to buckle, if it's going to bend this way. See, it's going to bend this way. It's not going to bend this other way. You want the smallest moment of inertia. Now, the moment of inertia about the axis going like this is 1/12, 2 inches times 4 inches cubed. You guys all know that. That's your equation. And we can get that. Go ahead and get that. Give me that moment of inertia. I'm going to do it. 1/12 times 2 times 4 cubed. I got 10.66. I'm getting 10.66 inches to the fourth for the moment of inertia that way. But see, you could also get the moment of inertia in this direction here. Usually they call this IX and this IY. And this is going to be 1/12. I did this wrong. This is IY and this is IX. This is going to be 1/12 4 times 2 cubed. Okay, do that. Let's see what we get. 1/12 times 4 times 8. I get 2.666 inches to the fourth. Well, if you had a 2x4, this is what you'd use. You always use the smallest one because it's easier. It's easier to bend about that x-axis. See, this we can call that the x-axis, and this we can call the y-axis. It's easier to bend that 2x4 about that x-axis than it is to try to bend it about the y-axis. What is the ratio there? What's that divided by 10.666? It's equal to, it's about 4-to-1. It's 4 times harder to bend this 2x4 about this x-axis. Okay, now wait a minute, I'm getting mixed up now. Yeah, about the y-axis. It's 4 times harder to bend it about the y-axis than it is the x-axis. I don't know if we understand that yet, but we're going to get there. Now let's work some problems. Now, I do need to tell you though that these can be supported in different ways. They have what they call pin supports. You're familiar with those, where you have smooth pins at the end. Pin supports. But they also have fixed supports. That's where maybe you have a weld. It's a completely different thing. See, this pin, when you compress this member, you can bend this member like this. So you can, but see, this won't bend like that. I tell you what this will do. This stays at 90 degrees. It's welded, let's say. And so what happens is you can have a buckling like that, but these stay at 90 degrees. They have different kinds of supports. They also have a fixed support and a pin support. Let's see if I can draw that. You could have a fixed support up here. They call this a fixed support. And maybe a pin support down here. Fixed support, pin support. So whatever happens up here, that 90 degrees stays 90 degrees. But this here, you can have a bend going on with that pin support. And they have what they call effective length. On page 675, if you have pin supports, the effective length is, they put a K in here. And they call K the effective length. It's on page 675. K is called the effective length. It all depends on how it's connected. Now, if they're both pins, we'll write it over here. If you have two pins, K is equal to 1. If you have two fixed ends, then K is equal to 0.5. And they have a couple of other possibilities. Let's just go to a problem now. I'm going to do this problem F13-2, but I need some room. Let me erase all this if I need the room. Now there's Euler's equation, and what they're asking us on problem 13, it's F13-2. They're asking us to do a 2x4. Well, we just did one, but this one's 12 foot long. Okay, it's 12 foot long. They give you the modulus of elasticity. That's nice of them. So look here, we know that. It's pin supported. So this K is just 1. If both ends have a pin, smooth pin. So we know that. We know the length. We know the K, we know the length. All we got to do is figure this I, and we got it made. Now there's two I's. One of them goes 1/12, 4 times 2 cubed for the I. And the other one goes 1/12, 2 times 4 cubed. We don't want that one. That's the big one. This is the small one. And so we just did that. I think it was 2.666, wasn't it? Let me do it again. No, I don't know what it was. Looks like it's, well, it's 8 divided by 3. Yeah, it's 2.666 inches to the 4th. So we know that. We know pi. We know K is 1. We know L. Now watch out though. This L is going to have to be, you'll have to convert it to inches. Here, let's write it out. I need some room here. Okay, we're going to find the critical load for this 2x4. Pi squared, 1.6 times 10 to the third KSI times 2.666 inches to the fourth divided by, that's a 1. L, if it's 12 foot, you're going to have to go 144 inches squared. Okay. Put that in your calculators. Let's find the critical load. Go for it. Well, I got an answer. Let me call on somebody. Ben Seaman, unmute and say hello to me, Ben.
Good morning.
What'd you get for the critical load when you plugged in these numbers?
I got 2.03 KSI.
That's not what I got. Now this won't be KSI. Now this is going to be in pounds. It's not stress. This is a load. It's going to be in pounds, or it might be in kips. But the load, what we're talking about here. Let me get some red color here. What we're talking about is if you push on this with enough force, this column will buckle. It's going to be in pounds. We're not talking about stress. Do it again, Ben. Put in these numbers and do it again. I'm going to do it again too. Maybe I goofed up. What'd you get this time, Ben?
I still got 2.03, but it'd be kips.
Did you square that pi?
Yes.
I have
I'll do
also
it
getting
again.
2.03.
Oh, you know what? I did it wrong. I bet Ben did it right. I did it wrong. I forgot to square this. Here I am telling, well, Ben, did you square that? I forgot to square the 144. Let me try it again. I bet you got it right. I got 2.03. What'd you say it was? What was your answer, Ben?
I got 2.03 kips.
That's what I got. Good going. You were right in the first place. Sorry to doubt you. Now, let's see how we did. Go to the back. This was fundamental problem 13.2. And go to the back and let's see what they say. Fundamental problem 13.2. 2.03 kips. Ta-da! Ben gets a big honking thank you point because he was right and the instructor was wrong. Let's do another one. Any question on that? Okay, I guess we're good. Let's do this one now. This is a 13.3. Let me make some room here. We're going to do problem. I just erased my Euler's equation. Dang it. We'll find it back. This is problem 13.3. I'm on page 679. Now this is not a 2x4 this time. It's a round rod. It's a circular rod. It's A992 steel. We're going to have to look up the E. Go to the back and look up the modulus of elasticity, and it says 29 MSI. Can you find it? 29 MSI? Actually, what it says is 29 times 10 to the third KSI. That's what it says, but it's the same thing as what I had. Okay, and did they give you the diameter? It says, oh, we have to find the diameter. Now, what they want is they want it to be able to handle 4 kips. Here, let's write the equation. Here's the equation. They want it to be able to handle 4 kips. So we're going to plug in some numbers here. This is going to be 29 times 10 to the third KSI. And the L is 18 inches. See it? 18, but you have to square it. Now, remember, I forgot to square it last time, and I got the wrong answer. But my student didn't. Now the I is going to be, if you look in the flap of your book, the I is for Ix is 1/4 pi r to the 4th. See if you can find that. See if you can find that equation for the I. For something round like this, the moment of inertia is 1/4 pi r to the 4th. It's in the flap of your book. I don't know if you can see this or not. See, in the flap of your book, see this, there's a round one. It says 1/4 pi r to the 4th. Okay. Hey, look, here's an equation with only one unknown. Look, we know everything except this r. We're going to find it. Now I'm going to shut up, and you have a minute and a half or whatever. I want you to find the radius. See, that would be the radius. Now, if you read the problem, I think they want the diameter. Yeah, they want the diameter. However, if we can find the radius, we can find the diameter, right? We'll just multiply the radius by 2 and we'll get the answer. Go for it. I'll be quiet. Well, I did that and I got a radius. Let me go to one of my students here and see. Braxton, unmute and say hi, please.
Hello.
Hey, Braxton, did you get this radius yet from this equation?
I think so. I got 0.2756 inches.
That's what I get. I got 0.2756 inches. Now, if you want the diameter, just multiply that by 2. I'm getting 0.5511 inches for the diameter. Now, if you read the problem, they want the smallest diameter to the nearest 1/16 of an inch. Okay, well, let's go to the hardware store now. And we're going to look and see what they have. Now, if you had a 1/2 inch diameter, that's a 1/2 inch. A 1/2 inch diameter is 0.5, and that's too small. You know what that is? That's 8/16, isn't it? If you had an 8/16 inch rod, that's a 1/2 inch, and that's too small. It would buckle. It would buckle. Now, if you had a 9/16 inch rod for the diameter, let's see what 9/16 is. 9/16 is 0.5625 inches. Hey, that's big enough. That's going to work. That's your answer. You have to have a 9/16. Tell the guy at the hardware store you want a rod that's 9/16 inches in diameter. And go to the back and let's see how we did. This was problem. Gee, I don't remember what problem it was. Yeah, it was problem 13.3. We just did 13.3. And I'm going to see what they say is the answer. Here we go, 13.3. The answer book says 9/16 of an inch. That's what the book says. They say it's 9/16 of an inch. And we'll be able to handle that load without buckling. You don't want any bigger than that 4 kip, so you might have a problem. Okay, well, we got into buckling, which I think is important. And I think you've got some homework there. I'm going to look that homework up because I got confused. Any last comments or questions? We're going to say bye for now until Thursday at 9:30. Any last words? Go ahead. Well, okay. Do that more circle homework. I guess you only have 2 problems, you lucky people. And I will see you Thursday morning. Bye-bye for now.
Goodbye, Mr. Griffin.
Yep. Ta-ta.